This is the last example regarding colligative properties that don't involve the Van Hoff factor, which we'll see in the next few slides. And this one allows us to calculate molecular formula similar to what we did back at the beginning of the year. When we calculate molecular formula, we need to be able to know what the mass is of that molecular substance compared to its empirical substance. Anthraquinone in this example is the solute, and it's being dissolved in the solvent camphor. And that's at the very bottom of your page. I promise, solute is anthraquinone and the solvent is camphor. So to calculate the molar mass of the molecular formula, we're going to need its grams and its moles. We already know the molar mass of the empirical formula using atomic masses to determine that with CS7H4O. And we know the mass of our anthraquinone, the 1.32 grams. So with that information and knowing how anthraquinone depresses the freezing point, we can determine the moles of the anthraquinone by calculating molality with our colligative property equation. We know the temperature change. It says that the freezing point of camphor was lowered by 22.3 degrees Celsius, so that is a change, not a specific temperature. When the 1.32 grams of anthraquinone was dissolved in the 11.4 grams of camphor. So we can use the delta T and our constant K for camphor, which I don't appear to have given to you in the problem. I'm sorry about that. I promise I would give that to you. It's 40 degrees Celsius per molal, and we multiply that by the molality, and when we do the math through, we get that the molality of this solution is 0.56 moles per kilogram. So that's 0.56 moles of anthraquinone for every kilogram of camphor, but we only had 11.4 grams of camphor. So to find the moles of just the anthraquinone, we need to multiply again the molality by the mass of the solvent in kilograms. And when we do that, we get our moles, 0.0064 of anthraquinone. Taking that amount and dividing 1.32 grams by it will give us the molar mass of our empirical formula, of our molecular formula, which is 206.25. Dividing that into the molar mass of the empirical formula gives us a ratio of 2 to 1, which is telling us that our molecular formula is approximately twice as big as our empirical formula. So when I substitute 2 in for that N value, I get that I would have C14H8O2 as the chemical formula for anthraquinone in its molecular form. If you need to pause, I would do so now. Osmotic pressure takes a look at how things flow through a membrane. We tend to hear about osmotic when you are cleaning your contacts. Those of you who wear contacts, you put them in a solution that's isotonic so that there isn't a net difference between what's in your contact and in the solvent. So you shouldn't see them swell or shrivel. But if you leave them out over a period of time, you will see them shrivel because they will be losing water. So osmotic pressure is just the excess pressure on the solution when you have a solute dissolved in it compared to the solvent. This equation may look similar to your ideal gas law. Pi, because we're dealing with pressure, is equal to the molarity, the constant, and temperature. So this basically is ideal gas law. We've just moved volume over to the right side of our equation by putting moles per liter, which is our molarity. We need to use our constant in atmospheres and a Kelvin temperature since we are using 0.08206 for our constant. We have 20 milligrams of a protein. It's dissolved in water to make 25 milliliters of a solution. The osmotic pressure of the solution is 0.56 torr at 25 degrees Celsius. What is the molar mass of our protein? So we're trying to calculate molar mass. We know the mass of the protein, so we need to find the moles of the protein. Molarity is the best part of osmotic pressure that's going to help us find moles. So we convert our 0.56 torr into atmosphere so we can use our gas constant and then multiply by our Kelvin temperature. Canceling out the units that are going to disappear, we'll be left with our molarity, which is 0.000030 moles per liter, or 3.0 times 10 to the negative fifth. This molarity is the moles of the protein dissolved in the solution, and since we had 25 milliliters of solution, we can multiply that by that in liters to get the amount of protein in moles, 7.5 times 10 to the negative seventh. If we convert the milligrams into grams and then divide that into the moles of the protein, we will get its molar mass. So that would be 20.0 milligrams divided by 1,000, which would give me 0.0200 grams. Divide that by 7.5 times 10 to the negative seventh moles, and you will get 27,000 grams per mole. And correct me if I'm wrong, Kai and Damien, I think I came up with it now. I think it's Dalton's is what we use to represent mass when you're dealing with larger biomolecules like proteins. If you need to pause, please do so now. So the Hoff factor is dealing with that number of particles that we talked about before, how it doesn't matter what the substance is, it matters how many particles it's able to provide. And so salt, because 1 unit of salt would break into 2 separate ions, would provide 2 particles. Potassium sulfate would break into 3 particles, 2 potassiums and 1 sulfate ion. And so to calculate the temperature depression or the osmotic pressure change in response to the number of particles, we include in our various equations and factor I, which is put on the side with both the molarity and the molality. So now you see pi is equal to I mart, and delta T is equal to I times your freezing or boiling point constant times the molality. So I have here 3 different solutions. We have sucrose in water with a molality of 0.01, salt in water with a molality of 0.01, and calcium chloride in molality with 0.01. And we want to take a look at which one of these would give us the highest freezing point. So the highest freezing point is the one that's going to be depressed the least. So if we take a look at these 3 substances, we would see that sucrose will not break apart since it's a molecular substance, it's non-electrolytic. So it would have an I value of 1. Salt would break into both sodium and chlorine ions, so that would have an I value of 2. And calcium chloride would break into 1 calcium and 2 chlorine ions, which would give me an I value of 3. So the one with the smallest I value is going to cause the freezing point to lower the least, which means it would have the highest value, and that would be the sucrose. Oh, sorry, I didn't realize I had pure water. My bad. Sucrose, although it will not have a substantially different I value from water, it will interfere with the water being able to kind of arrange itself just slightly, so it'll be a little tiny bit lower than water. I apologize for not recognizing that water was one of my choices as well. The pure solvent will always win out. The lowest freezing point will be the one that has the greatest I value, because it's the one that's going to interfere the absolute most with the solid being able to form, and that will be calcium chloride. And this is because they're all at the same molality. If they were in different molalities, you would have to compare the I value to the concentration and determine which one is having a greater impact, or what the product of those two would yield the greatest impact. The highest boiling point, if freezing point is being depressed, our high boiling point would be elevated when we have a greater I value, because it's going to make it more difficult for that liquid to be able to escape and become a gas. So this too will be calcium chloride. The one with the lowest boiling point, again, is going to be the one that least affects the boiling process, so that will just be pure water. So hopefully you're noticing that the smaller your I value, the less you are to affect your properties, unless you don't have an I value at all because you are the pure solvent. The highest osmotic pressure will be the substance with the greatest number of particles, so again, that'll be calcium chloride. And I don't know if I have another one or not. Sorry, I have 2 C's on there. Yep, that's it. And I believe this is our last slide. Here we're going to take the freezing point of solution A and the boiling point of solution B and calculate both of these. The first one we're going to take a look at is the freezing point of A, which is 0.250 molal AlBr3. And remember, water freezes at 0 degrees Celsius. So if we include our I value in our freezing point depression equation, We would have an I for aluminum bromide of 4, because aluminum bromide would dissociate into 1 Al plus 3 ion and 3 Br minus 1 ions. We have our constant K, 1.86 degrees Celsius per molal, and we have our molality, 0.25. The molalities cancel out, and we see that that depressed the freezing point. Okay, I just saw 4 times 1.86 and was like, whoa, hold on. But 4 times 0.25 is 1. So the temperature changed by 1.86 degrees. If it depressed it, it had to go down by that amount, so the freezing point of water would now be negative 1.86 degrees Celsius. For Ki, I'll go back for a second. If you need to pause, please do so now. And our last one's going to involve potassium iodide. We're going to find the boiling point of this solution. So we have our K constant. Ki will dissociate into 2 ions, potassium and iodide, 1 of each. So our I will be 2 this time, and that should be Kb, so please make a note of that. It should be I times Kb times M. The Kb would be 0.52 degrees Celsius per molal, and that'll be multiplied by the molality, 0.125. The molalities cancel out, and we multiply across, and we get the temperature did not change substantially. It only went up 0.13 degrees Celsius. Water boils at 100 degrees Celsius, so bumping it up 0.13 would give you a new boiling point of 100.13 degrees Celsius. If you need to pause, please do so now. Thought that was it, but I just wanted to double check. So that's the end of chapter 14, and that is the last new material for this year.